Okay, this is lesson 3.6, zeros and the discriminant. In the last lesson, we looked at how we could solve a quadratic and find the roots. In this lesson, we're going to look at how we might end up with different types of solutions. And when solving a quadratic, we could end up with 0, 1, or 2 real roots. And the number of our roots is going to be determined from a couple things, the location of the vertex relative to the x-axis and the direction it opens. Alternatively, we could use the sign of the discriminant. So you might ask what the discriminant is. Well, the discriminant is the part of the quadratic formula underneath the square root sign. And the reason that dictates how many solutions we have is because if you were to square root any positive number, you would get an answer. And then finishing this solution of the quadratic equation, you would take your negative b and add or subtract that positive answer, and that would create two different answers. So we'd get algebraically two real solutions. Alternatively, if the discriminant was to be 0, when you square root 0, you get 0. Adding 0 and subtracting 0 are the same thing. So when you're solving using the quadratic formula, you'd only end up getting one answer. You could write it twice, but it would be the same number both times when the discriminant is 0. And the last option is if we end up with a negative underneath the square root, when we try to square root it, we get an error in our calculator. And that's because you can't take the square root of a negative number yet. So in that case, we say there are 0 real roots because we can't get a solution. How does that relate to x-intercepts of a quadratic? Well, if we were solving the equation of a quadratic function, we would be finding the zeros or the x-intercepts, potentially. And in the case of no real roots, that means we would have a parabola that would look like this. It wouldn't cross the x-axis. It'd either be above and open up, or it'd be below and open down. Another option is we could have the vertex on the x-axis, and in that case it would only touch once. And our last option is the vertex could be above and the parabola could open down, causing two x-intercepts, or the vertex could be below and open up, also causing two x-intercepts. So the point of this lesson is to be able to look at any form of a quadratic and figure out how many zeros there are going to be. So first, in standard form, the way we can tell is we use the discriminant, the b squared minus 4ac. And to get no solutions, we would have to get a negative number, and that would cause the error when trying to solve. So if the discriminant is less than 0. And remember, in standard form, you have your a, b, and c that you would put into the quadratic formula. It's the same a, b, and c for the discriminant. To get the one real root, that's when the discriminant equals 0. And again, because if we square root 0, we get 0. Adding 0 and subtracting 0 give you the same answer, only causing one real root. And 2 is for any positive answer. So anytime the discriminant gives you a positive. So we can use the discriminant if we're given an equation in standard form to figure out how many zeros we're going to have. If we're in factored form, you can also tell. The easy one is to do two real roots first. So if we had a factored form, let's say it looked like a x minus r x minus s. If you had two brackets and you had an r and an s that were different numbers, those would be the roots. So if you have a quadratic in factored form and it's written that way, that means there's two roots. X would be r and x would be s. Whatever r and s are, those would be your roots, and as long as they're different, that's two real roots. What would the factored form look like if there was only one real root? Well, it would look like x minus r, but there'd be two of the same bracket. So we might just write the same bracket squared. And we would have one root. And it would be whatever r is, that one bracket. You could write it twice, but it would be the same number both times. So it would look like factored form, except there'd be two of the same bracket, in which case we'd probably simplify it and write it squared. Coincidentally, that looks a lot like vertex form. And the reason it looks a lot like vertex form is because if you look at the one real root solution, it's the vertex that is the root. So vertex form would look the same too. I'm going to skip to this one. It would look like x minus h squared, and there would be no k because it wouldn't be shifted up or shifted down. So they actually look the same. H and R would represent the same number. So there's one real root when it's in vertex form if the k is 0, if it's not shifted up or down. What about factored form if there are no real roots? Well, conveniently, for the purposes of this course, we wouldn't write it in factored form. So we'd say, because we cannot factor, there would be no factored form. Now that's going to change next year when we start to use imaginary number sets. We will write it in factored form. But for the purposes of this course, if you can't factor it from standard form, it is because either you're getting not nice whole numbers and you have to use the quadratic formula, but also you might get a scenario where you get imaginary roots and there's no real roots, so you can't write it in factored form, because if you could write it in factored form, you'd expect to see those two x and r, r and s's, and those would be your two roots. So since you can't write it that way, we could assume that there is no real roots. And vertex form. What would vertex form look like if there's two roots? Well, looking at these sketches, we would have vertex form. And what do we notice? Well, we notice that either the vertex is above, so shifted up and opening down, or shifted down and opening up. So if it's shifted down, k would be negative, and if it opens up, a would be positive. If it's shifted up, k would be positive, and if it opens down, a would be negative. So the key here is, if you see a vertex form, and a and k have opposite signs, where you're going to have two real roots. And that's something that you could just sketch. You don't have to memorize that. You just see the equation and think, okay, it's shifted up and it opens down, so that means it's going to cross the x-axis twice. No real roots happen when you have a positive k and a is also positive opening up, or you have a negative k because you're shifted down and it opens down, so a is also negative. So if you have a vertex form, and a and k are the same sign, you will have no real roots. So if k is 0, one real root. If a and k are opposite signs, you get 2. If a and k are the same sign, you don't get any. All right, so let's use this to do a question. This is one of my favorite questions. I like questions with extra variables in them, and they're kind of like concepts, like, for what values of p will this function have only one x-intercept? Well, first off, ask yourself what form this is. This is standard form. So if we go look at our table up here, how can we tell we have only one x-intercept if we're in standard form? Well, if we're in standard form, the discriminant must equal 0. So that's what we know. We know the discriminant, b squared minus 4ac, has to be 0. Well, do we know a, b, and c? We don't know a, we do know b, and we do know c. So let's fill in what we have here and see if we can do something here. B is 4, so we got 4 squared minus 4 times a is p, and c is 3. So now you have an equation with only one variable. You can solve it, and then I'll tell you exactly what p would only give us one x-intercept. So move this back down. So let's solve it out. 4 squared is 16, and negative 4 times p is negative 4p times 3 is negative 12p. I'm going to add 12p to both sides, divide by 12, and reduce my fraction. If I divide top and bottom by 4, I get 4 over 3. So if p is 4 over 3, we'll get exactly one x-intercept. And you could do this question for 2 x-intercepts or no x-intercepts. And the way you do it is, if it was written the exact same way, you would just change this to a less than sign or a greater than sign, depending on which one, and solve it out. And say we did no real roots. No real roots happens when you have discriminant less than 0. So if we wrote less than 0, the solving would actually look the exact same, and at the very end we'd end up with 4 over 3 is less than p. Or if we read it this way, p is greater than 4 over 3. So if p is greater than 4 over 3, we're not going to have any real roots. And if we wanted to do 2 real roots, we put a greater than sign there, solve it out, and we'd have 4 over 3 is greater than p. But if you read it this way, p is less than 4 over 3. So if p is less than 4 over 3, we get 2 real roots. So that 4 over 3 becomes key. And depending on what the question is, you can just use the discriminant, solve it out, and come up with a solution for what p would have to be for certain different scenarios. Last thing I want to do is talk about the transformations and zeros. So if we use a, k, c, and d on the original quadratic, so let's write this out. We've got y equals a, k, x minus d squared plus c. And we use different transformations. It's pretty much like vertex form, right? K is just the extra one, the horizontal shift, or sorry, the horizontal compression and stretch. What effects would changing these numbers have on the number of zeros? Well, A can stretch or compress, and if we have this graph, if we stretch it or compress it, it's not going to change the fact that we only have one zero. In fact, if we reflect it upside down, it's also not going to change the fact that we only have one zero. Where A does have an effect is if we've shifted the graph up first. For example, say our graph had a C value that was positive, and our graph was up here. Our vertex, sorry, was up here. And if it was reflected upside down, we'd have 2 x-intercepts. If it wasn't reflected upside down, we would have no x-intercepts. So the reflection, or the direction of opening, can make a significant difference. So if there's a reflection, it can change the number of x-intercepts. What about K? K is horizontal stretching, compression, and reflection. So if we've got our parabola and we've stretched or compressed it, it's not going to change. If we shift it over and stretch or compress it, it's not going to change. If we shift it down and we stretch or compress it, it's not going to change. If we shift it down and we reflect it, it's still not going to change. K, in fact, has no effect. And D, shifting it left and right, also has no effect. If it has one x-intercept and we shift it to the left, it still has one x-intercept. If this was shifted down, it would have 2 x-intercepts. And then if we were to shift it to the left, it'd still have 2. So D also has no effect. What I'm trying to get at here is the only things that actually affect how many x-intercepts there are the reflection and the shift up and down. If you have a vertical shift, it can significantly change the number of zeros. For instance, if we had that original parabola and we shifted it up, it would have no x-intercepts instead of 1. And if we shifted it down and it opened up, we'd have 2 x-intercepts. So going up or down does change the number of x-intercepts. Okay, so what do we have to take away from this? Basically, A and C are the things that influence the number of zeros. Okay, the shift up, down, and the reflection. The horizontal transformations don't impact how many zeros you have. All right, that's it for lesson 3.6. Thanks for watching, and I'll see you next time.